Now we have the presentation of Rafael Magila de Souza. Is here. He is a doctorate student, a PhD student in the USP Ribeirão.
Hi, everybody. Good morning. My name is Rafael Magila de Souza. I'm a PhD student in the group of Professor Luis Gustavo Dias. And today, I'm going to be presenting a few results of the coarse-grained model of this ionic liquid, 1,2,3-methyl-imidazolium tetracyanoborate. And this project is part of the project 19. So to contextualize, I could not be present here in the last two meetings because I was in Canada in the group of Professor Mikko Kartunen, who collaborated with us together with Professor Leonardo. So to contextualize, the first step of our project is to develop a electrolyte based on ionic liquid, specifically in the tetracyanoborate annual. This first step we did last year, and now based on this model, we are going to develop a coarse-grained model. That's why I'm doing this. So to understand, our motivation behind our study, why do you want to study ionic liquids as electrolytes? Because we are looking for new rechargeable batteries based on alkali metal salts and alkaline earth metals like sodium, potassium, and even magnesium. And we are looking to new kinds of materials in this project for electrodes, and specifically in our case for the electrolyte media. Since we are looking for electrolytes, we have a wish list, as Ebner already said in the last talk. We need to dissolve the alkaline metal salts. The electrolytes should have low viscosities. They should be stable electrochemically, easy to synthesize, and low environmental impact. So ionic liquids, they usually are as a good candidate because they meet those needs. And they also have some disadvantages. Usually they have high viscosities between 20 and 40,000 cent Poisson, and just for comparisons, the viscosity of water, the solvent, the universal solvent, just 1 cent Poisson or around room temperature. And another disadvantage is that some anions of the whole spectrum of ionic liquids, they can complex with the alkaline metal cations. So because of these two disadvantages, we are looking into the cyanoanion family, specifically in the tetracyanoborate anion, because this anion, for an ionic liquid, it has a relatively low viscosity, and they usually don't tend to complex with the alkaline metal salts. Together, the counter ion of this anion in our study is the imidazolium cation. The structure is right there. So the first step, we did simulations, atomistic simulations of this electrolyte, and we measured different physicochemical properties of these electrolytes, such as density, viscosity, diffusion of the species, ionic conductivity, and measuring how these properties behave in different amounts of sodium and potassium salts and different amounts of polyethylene glycomolecules. The molecules show there, because these molecules, we use them as additive in these electrolytes, because these molecules can wrap around the cations, and this effect also promotes an increase in the ionic conductivity of the electrolyte and decreases the viscosity of the system. Both properties, therefore, are desired when you think as applying them as electrolytes. So I'm showing this just to make an introduction of the coarse-grained model, because our model is based on these results. I'm not going deep here, because the main focus is about the coarse-grained model. So why do we need coarse-grained models? Because when you think in process and phenomena occurring in different length and time scales, in our system, since we are talking about with more than 10,000 atoms, it's prohibitively, from the computation point of view, to simulate them with quantum methods, and even in some cases with empirical atomic force fields. So to move up on this length scale and time scale, we consider these coarse-grained models. So coarse-grained models, they merge a set of atoms into a single interaction site that we call BID. So the tetracyanoborate anion, the second molecule in blue, we represent the whole molecule as a single interaction site, a single BID, and it's readable in this model because the structure of the anion, the 4 ligands, they are equal attached to the central boron atom. The imidazolium cation in our model, it comprises 3 BIDs, one for the central ring, one for the ethyl moiety, and the last BID, the last interaction site, for the methyl moiety of the structure. So to conclude, our model has only 4 interaction sites instead of almost 30 atoms, as if you use an atomic model, the size of the system would be. So because of this reduction in the number of particles, we can move up on this scale and simulate longer process with a longer time. What about our model? How did we parameterize this model? What about the calibration of this model? So in the literature, we can find a lot of coarse-grained models for all the cations of the imidazolium family, but we can't find a proper model, a decent model for the tetracyanoborate anion. So as a starting point, we based our model in this work of Merle and co-workers. They did a coarse-grained model for the cation is the same as ours, the ethyl-methyl imidazole, but they use a tetrafluoroborate anion. So if you look carefully, the structure of both anions are very similar. 1 boron, 1 central boron atom, and 4 equal ligands. So because of that, we start from this model, and then we adjusted the sigma and epsilon parameters based on a Lennard-Jones potential that our model includes, together with a Coulombic potential. Our model for our coarse-grained model is also a reduced charge model as a adjusting parameter as the other Lennard-Jones parameters. So as I was saying, we did a lot of trials, simulations, searching for the best combination of sigma and epsilon parameters of our annual and the cross interaction between the two species. And the target properties of our calibrations were the properties such as density, diffusion coefficients, and viscosity. And of course, we did comparison with available experimental data and also our atom simulation data. This is still an ongoing work. We are in the middle of the work, so I'm showing here preliminary results. 4 graphics, one for each property, one for density, one for viscosity, and one for the diffusion of each species. So the first graphic of density, the results, the experimental results are in red, and the values with our model is in black, in dashed line. So the values of density in all this temperature range are very close to the experimental data, although the inclination of the curves are different. However, the errors, if you think in the absolute values of the properties, is just around 1 or 2%. So it's a satisfactory good model when we think about this first property. The viscosity, the second graph, in now the temperature range, the values are very close to experimental data. So our model satisfies very good the second property. And the diffusion coefficient, we have the first issue here is that we have experimental data only for 2 temperatures. So the comparison is not as precisely as if we had the values for all the temperature range. But in principle, our model is even better than the atomistic data that we use as reference for this tetracyanoborate annual. The values are very close. However, the main problem so far of this model is about the diffusion of the imidazolium cation. The values with this coarse-grained model are not so good if you compare to the experimental data. So during the calibrations, we can find specific parameters that can describe this property closer to the experimental values. However, all the other properties would be dramatically very affected. So we use an error function to minimize the error in our calibration between all these properties. So far, we have this little issue that we should try to correct. So as to conclude as next steps, can we improve the properties of this ionic liquid model? So we are going to add a few properties in the calibration, such as the partial molar volume of each of the ionic species, and then we can have a better direction if you can improve or not this model within this resolution. Another thing we should look is about the structural properties. I just looked at so far the transport properties of this ionic liquid. And then in the near future, since we're talking about electrolytes, we also want to include the sodium and potassium ions together with this model, and then we can perform multiscale simulations together with the electrode as well. So that's it for today. Thank you.
We are open for questions.
Hi, Rafael. Thank you for showing us these nice results. I was curious here because you told us that one of the motivations to use the coarse-grained model was to have more feasible computational costs in relation to other methods. But then you told us that you would compare your results to all atoms calculations. So these results exist. And I was wondering about what's the difference between your calculation. It's just that I didn't understand this motivation. What's the difference between the existing calculations and what you are doing? Please elaborate on that. Thank you.
Because this is the first step. We are calibrating the model. So we consider, in this case, our simulation around 500 ionic pairs. So it's not a very big system, but it's not very small. But we need to calibrate the model to describe the physical chemistry properties like the diffusion, the viscosity of the system. After that, we can increase the size of the system. We can simulate together with the electrode. We can add additives into the electrode and then expands the range of applications. This is just the first step to calibrate the model.
That can around the ion. That one, yes. Yeah. Are you thinking to do also the modeling of this molecule with coarse-grained?
It's a possibility. I don't know if I will have time because I'm about to conclude my PhD, but it's one of the goals of the project. Yeah.
More questions?
Well, thanks for the nice talk. For example, when you mentioned that you are trying to calibrate it, but you are using the properties like a very large macroscopic properties, like the diffusion, in which it's very hard to say put inside of the atomic understanding. How means because your potential can describe the atomic part in a very different way, but in the average might give the properties closer to the diffusion. How can you would say get out of those type of problems that can have during the setup of the calculations?
Sorry, I couldn't understand your
my concern is conceptual. How do you check up that you are using only the diffusion as a parameter to check if your parameterization of your potential is good or not?
It's not on the diffusion.
Yes.
We have the density, the viscosity, and as I said, in the end, we are also going to look into the structural properties. We can also measure other properties like conductivity, but when and then we can evaluate with more reference data if our model is good enough or not.
But when you mean by different additional data, all those data come from the same source of experimentals or theoretical, or are spread from the literature from different?
Okay. No. The experimental data, we just found 2 articles, 2 papers, and then we compiled this data, and the Awaram reference data is just one model that we have. Yeah. That's the problem with this kind of system. We have a few experimental data. The pure ionic liquid still can find some data, that's the case, but when you think in mixtures with sodium, polyethylene glycomolecules, the experimental data are very scarce, and then that's a problem for us.
Is there some alternative approach to avoid to use only those experimental data, but use sometimes, for example, a short scale, ab initio dynamics for like a very short, smaller system, short scale, if you could use to compare with your atomic calculations?
We could, but the cost computationally would be very big because we have a lot of systems with different amounts. If you think in the mixture, because we don't have experimental data of the mixture. We have a lot of systems, 22 compositions in my case, so to simulate with quantum methods, it would be very costly.
We have more questions.
Hello, thank you for your talk. I have a question regarding your anion model, because you took something that was a one atom centered, the one based from that boron fluoride anion. It's in the next slide, I think. Yes, that one. Do you have some reference to the validity of your model? For example, the one you're trying to model is more complex than the one you based on? Do you have a lot of some reference where that it's acceptable, suitable?
It's something that is usually done, but of course we need to, as a start point, as I said, we took the parameters of the first model, and then we need to find the right set of parameters of our model. Since the cation is the same, in the beginning, the first set of simulations, I didn't change the parameters of the cation, just of the anion. And then the parameters of the cross interactions, looking to find the better set of parameters that can reproduce the physical chemistry problem, because this is a top-down model. It's not based on it's not a bottom-up model based on a more fine-grained structure or a fine-grained model.
Okay,
So,
thank you.
We don't have time now. You can talk after that. Okay. Let's thank the speaker again.